Hi, my name is Apurva Manaraj. In this project for the Duke AI Product Management Specialization, I built a machine learning model to predict electrical energy output from a combined cycle power plant using environmental sensor data. Let me walk you through how I approached this problem. The goal was to predict the hourly net power output or PE of a combined cycle power plant. The data set includes 9,568 hourly measurements, each with four environmental features: ambient temperature, exhaust vacuum, ambient pressure, and relative humidity. PE, the power output, is a continuous numeric value, which means this is a regression problem. Since we are predicting a continuous value, I selected regression as my machine learning task. I used Google Vertex AI AutoML because it automates testing different algorithms, hyperparameter tuning, and data preprocessing. Additionally, since I hadn't used this tool before, it was a great opportunity for me to learn and upskill while working on this project. This actually allows non-programmers to develop robust models while still exploring different modeling strategies. For model building, I first uploaded the CSV data into Vertex AI. I set PE as the target column and kept all four variables as features. I split the data into 80% for training, 10% for validation during the training, and 10% as a final test set untouched until the end. This split ensures we evaluate model performance on unseen data. I allocated a budget of one node hour, but the training ran for about 2 hours, 10 minutes because AutoML tested multiple models and hyperparameters to optimize results. For evaluation, I chose RMSE, root mean squared error, as my primary metric because it reflects how much predictions deviate from actual values in the same units, megawatts, and penalizes large errors more heavily than the smaller ones. After training, my model achieved excellent results on the test set. RMSE of 3.313 megawatts, MAE of 2.561 megawatts, R square score of 0.961, MAPE only 0.566%. RMSE and ME both measure how close predictions are to the actual values. And RMSE score of about 3.3 means that on average predictions deviate by 3.3 megawatts from the true value. And R square of 0.961 means my model explains about 96.1% of the variability in power output, indicating a strong fit. In my model, ambient temperature was the most significant predictor at 58.38%. Exhaust vacuum was second at 27.1%. Ambient pressure contributed about 7.83%, and relative humidity had a smaller but relevant impact at 6.69%. This actually aligns with domain knowledge because temperature and turbine vacuum strongly influence thermal efficiency in power plants. From a business perspective, this model has several valuable applications: forecasting power output under changing environmental conditions, supporting operational planning and load balancing, helping reduce uncertainties in energy production. From a technical perspective, the model's low error rate means it's quite reliable. However, like any model, it might not capture extreme, rare conditions that are not seen in the training data. Based on the results, this model can reliably predict power output from environmental variables. In practical terms, this could help optimize operations in a power plant by anticipating how much power will be produced under specific conditions. Overall, the model demonstrates how machine learning can support better decision making in the energy sector. Thanks a lot for watching.